Okay, so let's talk about cardiac output. So we did cover cardiac output in terms of the heart by itself, and our formula for cardiac output is stroke volume times heart rate. So how much blood can you move through your heart in 1 minute? Now, because your heart is the pump, this is also tied to blood flow through your veins. So cardiac output, we abbreviate CO, but we're talking about something called hemodynamics, so basically how blood flows through your body. It's also sometimes abbreviated Q or Q with a dot, and this determines how fast blood flows through your vessel. Again, your heart is doing the pumping, therefore the activity of your heart and the flow from your heart is going to determine how fast your blood flows. So the big two factors that affect blood flow in general are pressure, and we talked about pressure, and then something called resistance. So blood flow, and sometimes in different textbooks you might see blood flow referred to Q, sometimes as F. I'm going to use it F for this slide, and what we have here is not an alpha, and it's not a fish, that's not an equal sign. This actually means blood flow is proportional to pressure, something we call pressure gradient, pressure drop. I put here pressure difference. I like to think of it as like gradient is a little more subtle, but I think it's when you're starting out, especially in physiology, it's basically what's the difference in pressure from point A to point B. Gradient implies that there's a little more different, like it's not so much like a big drop from one end to the other. But for now, just think of it as the difference between pressures between 2 points. And then that's over something called resistance. So basically, if you have your pressure gradient over resistance, that is proportional to your blood flow. Okay, so what does that mean? Well, for people, those of you who might be a little math phobic, what this means is like when you have, let's ignore resistance for now. In this part right here, if flow is proportional to pressure, if pressure goes up, flow goes up. So that's what it means. But what happens with so you have your numerator and your denominator. Denominator is the number on the bottom. So what happens if resistance go up? And notice that it's on the bottom. So we did say if pressure goes up, flow goes up. When the number is on the bottom in one of these proportions, it's actually as this goes up. Well, what happens if you have like, okay, go from 1 to 1/2 to 1/3 to 1/4 to 1/5 to 1/6 to 1/7? So what happens to that series of numbers? Notice that as the denominator gets bigger, the overall number gets smaller. So as resistance goes up and gets bigger, that's going to make this overall number smaller. Therefore, as resistance goes up, flow will go down. If resistance goes down, flow will go up. So this is proportional, but this is actually what we call inverse proportional. Inverse proportional means like two things. If one goes up, the other goes down. And if the other goes down, then the other one goes up. So that's inverse proportion with resistance. Okay, so more about the F. Also sometimes called Q, especially if you're going to advanced classes or if you're going to the medical field, there's a concept that you'll have to know called VQ matching. So when you see Q used in medical physiology, it's talking about blood flow, typically. So what happens here, again, with that proportionality, as you have more pressure, that's going to cause more flow. So this F and P, so flow and pressure are proportional to each other. But again, remember flow and resistance are inversely proportionate. So as resistance goes up, flow goes down. If resistance goes down, then flow goes up. So that's an inverse proportion. And sometimes it's simplified as, so things that even though I say it's proportional, when you're starting out, it might be easier to think of it this way. So sometimes instead of just saying proportional, you just say F equals P, delta P, or the pressure drop over resistance. Or if you do a little algebra, you can make it this way. So pressure equals flow times resistance. And this is one story I heard of why Q is called, or why blood flow is sometimes called Q, is because PQR. So based on that formula. I know, not very satisfying. It might not be very satisfying to you, but that's probably the most believable explanation I heard in terms of why blood flow is sometimes abbreviated as Q or Q dot. Okay, so then what generates pressure? Well, again, what's that big pump causing the pressure throughout all your vessels? It's from the contraction of your heart muscle, right? So by squeezing, that's going to squeeze all the blood inside the ventricles. That causes the blood to flow out due to the increased pressure inside the ventricles. Now, pressure gradient and the abbreviation delta P, sometimes called pressure drop. So it's a measure of overall circulatory pressure. So what is the difference between pressure where it's highest and where it's lowest? And what we see is that the delta P in your entire circulatory system, or when we're talking about systemic pressure, is that where's the pressure the highest? Well, what's the vessel that's closest to your heart, or leads from your heart? Yeah, your aorta, right? And blood travels through your aorta, through your arteries, then to your arterioles, to your capillaries, to your venules, to your veins, then to your vena cavae, which lead to your right atrium, right? So this is where it starts to leave the heart, and this is where it returns to the heart. So we have your highest pressure at the heart, lowest pressure at the right atrium. So the overall pressure gradient of your systemic circulation, this is how you calculate it. The pressure between the aorta and right atrium. Now to make it more visual, what we have here, again, blood leading away from your heart. And notice that, again, pressure is greatest near the heart and then drops off near the vena cavae. So that pressure gradient is going to be basically where it's highest to where it's lowest. So if point A is here, point B is here, that delta P of your entire systemic circuit is going to be the difference between the pressure at your aorta, and right after here, the vena cavae, remember, they lead to the right atrium, so this is going to be roughly equal. That's your pressure gradient. So again, aorta minus the right atrium pressure.